property graphs. In the property graph model, each vertex consists of a unique identifier, a set of outgoing edges, a set of incoming edges, a collection of properties key-value pairs. Each edge consists of a unique identifier, the vertex at which the edge starts the tail vertex, the vertex at which the edge ends the head vertex, a label to describe the kind of relationship between the two vertices, a collection of properties key-value pairs. You can think of a graph store as consisting of two relational tables, one for vertices and one for edges. As shown in example 2-2, the schema uses the PostgreSQL JSON data type to store the properties of each vertex or edge. The head and tail vertex are stored for each edge. If you want the set of incoming or outgoing edges for a vertex, you can query the edges table by head vertex or tail vertex, respectively. Example 2-2, representing a property graph using a relational schema. Some important aspects of this model are: any vertex can have an edge connecting it with any other vertex. There is no schema that restricts which kinds of things can or cannot be associated. Given any vertex, you can efficiently find both its incoming and its outgoing edges, and thus traverse the graph, i.e. follow a path through a chain of vertices both forward and backward. That's why example 2-2 has indexes on both the tail vertex and head vertex columns. 3. By using different labels for different kinds of relationships, you can store several different kinds of information in a single graph, while still maintaining a clean data model. Those features give graphs a great deal of flexibility for data modeling, as illustrated in figure 2-5. The figure shows a few things that would be difficult to express in a traditional relational schema, such as different kinds of regional structures in different countries. France has departments and regions, whereas the US has counties and states. Quirks of history such as a country within a country, ignoring for now the intricacies of sovereign states and nations, and varying granularity of data. Lucy's current residence is specified as a city, whereas her place of birth is specified only at the level of a state. You could imagine extending the graph to also include many other facts about Lucy and Elaine, or other people. For instance, you could use it to indicate any food allergies they have by introducing a vertex for each allergen, and an edge between a person and an allergen to indicate an allergy, and link the allergens with a set of vertices that show which foods contain which substances. Then you could write a query to find out what is safe for each person to eat. Graphs are good for evolvability. As you add features to your application, a graph can easily be extended to accommodate changes in your application's data structures. The Cypher Query Language. Cypher is a declarative query language for property graphs, created for the Neo4j graph database. It is named after a character in the movie The Matrix and is not related to ciphers in cryptography. Example 2-3 shows the Cypher query to insert the left-hand portion of figure 2-5 into a graph database. The rest of the graph can be added similarly and is omitted for readability. Each vertex is given a symbolic name like USA or Idaho, and other parts of the query can use those names to create edges between the vertices. Using an arrow notation, Idaho: within USA creates an edge labeled within, with Idaho as the tail node and USA as the head node. Example 2-3. A subset of the data in figure 2-5, represented as a Cypher query. When all the vertices and edges of figure 2-5 are added to the database, we can start asking interesting questions. For example, find the names of all the people who emigrated from the United States to Europe. To be more precise, here we want to find all the vertices that have a born in edge to a location within the US and also a living in edge to a location within Europe, and return the name property of each of those vertices. Example 2-4 shows how to express that query in Cypher. The same arrow notation is used in a match clause to find patterns in the graph. Person: born in matches any two vertices that are related by an edge labeled born in. The tail vertex of that edge is bound to the variable person, and the head vertex is left unnamed. Example 2-4. Cypher query to find people who emigrated from the US to Europe. The query can be read as follows. Find any vertex, call it person, that meets both of the following conditions. Person has an outgoing born in edge to some vertex. From that vertex, you can follow a chain of outgoing within edges until eventually you reach a vertex of type location, whose name property is equal to United States. That same person vertex also has an outgoing lives in edge. Following that edge, and then a chain of outgoing within edges, you eventually reach a vertex of type location, whose name property is equal to Europe. For each such person vertex, return the name property. There are several possible ways of executing the query. The description given here suggests that you start by scanning all the people in the database, examine each person's birthplace and residence, and return only those people who meet the criteria. But equivalently, you could start with the two location vertices and work backward. If there is an index on the name property, you can probably efficiently find the two vertices representing the US and Europe. Then you can proceed to find all location states, regions, cities, etc. in the US and Europe respectively by following all incoming within edges. Finally, you can look for people who can be found through an incoming born in or lives in edge at one of the location vertices. As is typical for a declarative query language, you don't need to specify such execution details when writing the query. The query optimizer automatically chooses the strategy that is predicted to be the most efficient, so you can get on with writing the rest of your application. Graph queries in SQL. Example 2-2 suggested that graph data can be represented in a relational database. But if we put graph data in a relational structure, can we also query it using SQL? The answer is yes, but with some difficulty. In a relational database, you usually know in advance which joins you need in your query. In a graph query, you may need to traverse a variable number of edges before you find the vertex you're looking for. That is, the number of joins is not fixed in advance. In our example, that happens in the colon with an asterisk 0 rule in the Cypher query. A person's lives in edge may point at any kind of location: a street, a city, a district, a region, a state, etc. A city may be within a region within a state within a country, etc. The lives in edge may point directly at the location vertex you're looking for, or it may be several levels removed in the location hierarchy. In Cypher, colon within asterisk 0 expresses that fact very concisely. It means follow a within edge 0 or more times. It is like the asterisk operator in a regular expression. Since SQL 1999, this idea of variable length traversal paths in a query can be expressed using something called recursive common table expressions, though with recursive syntax. Example 2-5 shows the same query finding the names of people who emigrated from the US to Europe expressed in SQL using this technique supported in PostgreSQL, IBM DB2, Oracle, and SQL Server. However, the syntax is very clumsy in comparison to Cypher. Example 2-5. The same query as example 2-4, expressed in SQL using recursive common table expressions. First, find the vertex whose name property has the value United States, and make it the first element of the set of vertices in USA. Follow all incoming within edges from vertices in the set in USA, and add them to the same set, until all incoming within edges have been visited. Do the same starting with the vertex whose name property has the value Europe, and build up the set of vertices in Europe. For each of the vertices in the set in USA, follow incoming born in edges to find people who were born in some place within the United States. Similarly, for each of the vertices in the set in Europe, follow incoming lives in edges to find people who live in Europe. Finally, intersect the set of people born in the USA with the set of people living in Europe by joining them. If the same query can be written in 4 lines in one query language but requires 29 lines in another, that just shows that different data models are designed to satisfy different use cases. It's important to pick a data model that is suitable for your application. Triple stores and SPARQL. The triple store model is mostly equivalent to the property graph model, using different words to describe the same ideas. It is nevertheless worth discussing, because there are various tools and languages for triple stores that can be valuable additions to your toolbox for building applications. In a triple store, all information is stored in the form of very simple 3-part statements: subject, predicate, object. For example, in the triple Jim likes bananas, Jim is the subject, likes is the predicate verb, and bananas is the object. The subject of a triple is equivalent to a vertex in a graph. The object is one of two things: a value and a primitive data type, such as a string or a number. In that case, the predicate and object of the triple are equivalent to the key and value of a property on the subject vertex. For example, Lucy, age 33 is like a vertex Lucy with properties age:33, another vertex in the graph. In that case, the predicate is an edge in the graph. the subject is the tail vertex, and the object is the head vertex. For example, in Lucy, married to Elaine, the subject and object Lucy and Elaine are both vertices, and the predicate married to is the label of the edge that connects them. Example 2-6 shows the same data as in example 2-3, written as triples in a format called turtle, a subset of notation 3 and 3. Example 2-6, a subset of the data in figure 2-5, represented as turtle triples. In this example, vertices of the graph are written as some name. The name doesn't mean anything outside of this file. It exists only because we otherwise wouldn't know which triples refer to the same vertex. When the predicate represents an edge, the object is a vertex, as in Idaho within USA. When the predicate is a property, the object is a string literal, as in USA name United States. It's quite repetitive to repeat the same subject over and over again, but fortunately you can use semicolons to say multiple things about the same subject. This makes the turtle format quite nice and readable. See example 2-7 Romans 7. Technically, the Atomic uses 5 tuples rather than triples. The 2 additional fields are metadata for versioning. Example 2-7. A more concise way of writing the data in example 2-6. The semantic web. If you read more about triple stores, you may get sucked into a maelstrom of articles written about the semantic web. The triple store data model is completely independent of the semantic web. For example, Datomic is a triple store that does not claim to have anything to do with it. Romans 7, but since the two are so closely linked in many people's minds, we should discuss them briefly. The semantic web is fundamentally a simple and reasonable idea. Websites already publish information as text and pictures for humans to read. So why don't they also publish information as machine-readable data for computers to read? The Resource Description Framework (RDF) was intended as a mechanism for different websites to publish data in a consistent format, allowing data from different websites to be automatically combined into a web of data, a kind of internet-wide database of everything. Unfortunately, the semantic web was overhyped in the early 2000s, but so far hasn't shown any sign of being realized in practice, which has made many people cynical about it. It has also suffered from a dizzying plethora of acronyms, overly complex standards proposals, and hubris. However, if you look past those failings, there is also a lot of good work that has come out of the Semantic Web project. Triples can be a good internal data model for applications, even if you have no interest in publishing RDF data on the Semantic Web. The turtle language we used in example 2-7 is a human-readable format for RDF data. Sometimes RDF is also written in an XML format, which does the same thing much more verbosely. See example 2-8. Turtle/N3 is preferable as it is much easier on the eyes, and tools like Apache Gina can automatically convert between different RDF formats if necessary. Example 2-8. The data of example 2-7 expressed using RDF/XML syntax. RDF has a few quirks due to the fact that it is designed for internet-wide data exchange. The subject, predicate, and object of a triple are often URIs. For example, a predicate might be an URI such as http://mycompany.com/namespace#within or http://mycompany.com/namespace#livesin, rather than just within or livesin. The reasoning behind this design is that you should be able to combine your data with someone else's data, and if they attach a different meaning to the word within or livesin, you won't get a conflict, because their predicates are actually http://other.org/foo#within and http://other.org/foo#livesin. The URL http://mycompany.com/namespace doesn't necessarily need to resolve to anything. From RDF's point of view, it is simply a namespace. To avoid potential confusion with HTTP URLs, the examples in this section use non-resolvable URIs, such as earn:\example:\within. Fortunately, you can just specify this prefix once at the top of the file and then forget about it.